Hey, welcome to 4.2. This is the second section in chapter 4. We do 3 of them. This one is a follow-up to what we learned last about divisibility, and it's all about prime and composite numbers. There are quite a few things in here you should know already, so hopefully this goes pretty quickly. The standards in here are all about finding factor pairs, so the numbers that you can multiply together to make a number. And determining if a number within 1 digits, 2 digits, 3 digits, and so on is a prime number or is a composite number. So to define those, a prime number is a natural number, okay? So something you can count on your fingers, and it is greater than 1, but only divisible by 1 in itself. 3 is a prime number, 7 is a prime number, 11 is a prime number. You could name a whole bunch, 19. A composite number is also a natural number, but it is a number that is divisible by 1 itself and at least one other thing. So 4 is divisible by 1, 4, and 2. 9, right? 10. So there's lots and lots of primes and lots of composite numbers. Numbers are either one or the other, with the exception of 1. It is a unit rather than prime or composite. So this is actually like one of those weird questions that shows up on standardized tests a lot. They ask you whether 1 is prime, composite, or neither. The answer is neither. Okay, so one of the things we have to do is determine if numbers are prime or composite. So take a look at the numbers on this list and see if you can figure out if they are prime or composite or what. Okay, and then think about how you did that. So for the first one, I know immediately this one is prime. How do I know? Or sorry, not prime, composite. This is a composite number. Immediately, I know that because I know it's an even number and it's divisible by 2. So if it's divisible by 2, it's divisible by at least something besides 1 and the number of 1,564. What about 1,001? Well, it's not divisible by 2, by 3, by 4, by 5. If it's not 2 and 3, it's not 6. 7, we'd have to actually divide. 8, I don't know. Nope. 9, not 10. 11, we ought to check though, right? So if we add the odd place, even places, and odd places, let's see. That's a 1 plus nothing minus a 1 plus nothing. That's going to get me nothing. Oddly enough, 11 is divisible, or 0 is divisible by 11, right? So it's just 0. So that makes this divisible by 11, okay? So we can write it like we were using the notation last time. 1,001 is divisible by 11. If that's the case, it's composite. All right, 2,781. Well, use your tests. Is it divisible by anything you can think of? Well, I know it's not even, but let's add the digits. 2 and 7 is 9, 8 and 1 is 9, 18. 18 is definitely divisible by 3. It would be divisible by 3 and by 9. So this is, again, going to be composite. Now look at the last one. Here's the thing. You don't have to multiply it all the way out, okay? So think about what you have here. I know 3 times 5 is going to get me 15. That's going to be an odd number, right? And then let's see. 15 times 7 is going to get me an odd number. It's 105. Times another odd number with an 11, also odd. Times another odd number, going to be also odd. Okay, odd times odd times odd times odd. I have an odd number of odds. This is going to end me up with a number that's odd. But what do I have to do to it at the end of it? I have to add a 1, right? So if I take an odd number and I add 1, what kind of number do I get? Well, I get an even number. And all even numbers we know are divisible by 2. So this number here, whatever it happens to be, is divisible by 2. So it is also composite. Okay? So there's lots of ways to figure out prime and composite. mostly we think through our divisibility rules and what we know about numbers, right? There's a reason we talk about all these things. When we want to look at composite numbers specifically, we can write them as a product of their prime factors. This is when we use prime factorization. We can use factor trees or division. Mostly my guess is you guys will use factor trees, okay, because that's where your experience is. So if we think about the number 900, this is a factor tree. So we think about 900, we break it up into 9 and 100, right? I can break down 9 into 3 times 3, and those are prime. I can break 100 into 10 times 10. Those are not prime, so I need to break them down again. I break them into 2 and 5 and 2 and 5. So when I'm finished, what I do is I write out my prime factorization as powers of prime factors. So I have 2 squared because I have 2 2's. I have 3 squared because I have 2 3's. And I have 5 squared because I have 2 5's. Okay, so that is the prime factorization of 900. So now let's try another one. This says 900. It should say 720. So let's do the prime factorization. Take a minute of 720. There's lots of ways to do it, but you know, in the end, you should end up in the same place no matter how you start. So let's see. I'm going to do 720. I'm going to think about it as 90 times 8, right? So then I'm going to break down my 90, and you might have done it different, that's okay, into 9 and 10. So I'm going to break 9 into 3 and 3. I'm going to break 10 into 2 and 5. Those are all prime. 8 is not made up of primes yet, so I have a 2 and a 4, and then a 2 and a 2. So now we look at where our branches ended. Here, 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 and here. And we count everything up. I have 1, 2, 3, 4 2's, 2 to the 4th. And we write them in increasing order generally. I have 2 3's, and I have a 5. Okay, so that's the prime factorization of 720. You can do this for lots of different numbers, and you will. One of the things, this is just what we just did. The primes in a prime factorization of number are usually listed in increasing order from left to right. If it appears more than once, we write it with an exponent. That's what we just did right here. We wrote increasing order with exponents, okay? One of the other things we can figure out once we can break up a number is how many divisors it has. When we're talking about divisors, we're talking about the number of things that divide into that number evenly. So think about all of the different ways that you could make 24. Okay, so if I have the number 24, I could do, I don't want that. I could do 1 and 24, right? I could do 2 and 12. I could do 3 and 8. I could do 6 and 4. Those are all things that divide evenly into 24. Well, how many are there? 1, 2, 3, 4, 5, 6, 7, 8. So 24 has 8 divisors. That's it. Here's the thing though, it's not always that easy, is it? If I have a bigger number, that's a little more complicated. So this is an easy example to start with, but it's going to get crazier from there. So the way we do that is through prime factors. So if we take 24 and we think about its prime factors, let's break up 24. You can do it any way you want. I'm going to use, I don't know, 12 and 2. 12 breaks up into 3 and 4. 4 breaks up into 2 and 2. So I have my prime factors. I have a 3, a 2, a 2, and a 2. So that's 2 to the 3rd times 3. Okay, great. Well, there's this rule, and it says if P and Q are different primes and N and M are whole numbers, then P to the N, Q to the M, okay? And we just wrote something like that, didn't we? 2 to the 3rd, 3 to the 1st. That represents 24. That's the prime factorization of 24. Then P to the N, Q to the M has N plus 1 times M plus 1 whole number divisors. okay? So basically what this says is no matter how many things you multiply together, if they're prime, and they're to an exponent, you add up the exponents, each one plus 1, multiply them together, and that's the number of divisors. So in this case, I would take my exponent on my 2 is a 3, plus 1 gets me 4, okay? My exponent on my 3 is a 1, plus 1. So this is going to be 4 times 2. That's going to get me 8. That's the number of whole number divisors that 24 has. We already saw that because we figured them out. So now that means if we have a bigger number, we can find out the number of prime factors and whole number divisors, okay? So to get the number of whole number divisors, we prime factorize it. We do the prime factorization, and then we calculate, okay? So you try these two, please. Now it is useful to think in exponents when you can. So for me, you can break this down into 1,000 times 1,000 and 100 times 100. You can do this. 100 times 10, I lie. And then break that into 10 and 10 and 10 and 10. Well, this is 1, 2, 3, 4, 5, 6, 10 to the 6th, okay? Well, 10 is not a prime yet, is it? So I have 6 10s, but I can actually think about 10 to the 6th. Use our exponent rules, right? 10 to the 6th is the same as 2 times 5 to the 6th, isn't it? That's a little tiny 6. Then that's the same as 2 to the 6th times, that's a 2, times 5 to the 6th. All right, well now I have what I need set up to do my whole number divisors. So I look at my exponents, 6, and then I add 1 is 7. And I look at the 5, it has 6 and 1 is 7. 7 times 7 is 49. So the number, a million, has 49 whole number divisors. There are 49 numbers that divide into a million evenly. Huh. All right, so let's look at 210 to the 10th. Well, we're going to ignore the exponent for a second. We're just going to deal with the 210. Break up 210. So I can make that into 70 and 3. I can make that into 10 and 7. And then I could make that into 2 and 5, right? So on the inside of the parentheses, I have 2 times 5 times 3 times 7. But each one is to the 10th. So 2 to the 10th times 5 to the 10th times 3 to the 10th times 7 to the 10th. So now to figure out the number of prime or divisors, I add 1 to each exponent. That's going to be 11 times 11 times 11 times 11. It's going to be a whole lot of divisors. That's going to be 11 to the 4th. And if you want to leave that right there, that's fine. I don't need you to know off the top of your head what 11 to the 4th is. I can tell you that it's 14,641, but you don't need to calculate that, okay? But that's a lot of whole number divisors. But think about how big this number is. 210 to the 10th power. It's a really big number, so it makes sense that it has a lot of divisors. All right. If D is a divisor of N, then N divided by D is also a divisor of N. This is a rule we actually saw in the last, in 4.1, just written a little differently. This is where it says that if, remember, 3 divides into 12, 3 also divides into 24. 3 also divides into 36. 3 also divides into 48. It divides into multiples of that, okay? So basically what this says is if we can take a number and determine what it's divisible by, it can help us figure out if it's prime, okay? We test the numbers we have, really 0 through 11, and then everything else is kind of a multiple of one of those numbers except for primes. So that gets us most of the way there. The second thing that gets us all the way there is that there is this rule. If n is composite, then n has a prime factor p, such that p squared is less than or equal to n. Okay? So if n is composite, there's a number, p squared, a prime number squared, that is less than or equal to n that is a prime factor. Okay? Sounds crazy, but here's what we're going to do. We're going to try it. So, there's a second theorem, and then my example is on the slide. If n is a whole number greater than 1 and not divisible by any primes p such that p squared is less than or equal to n, then n is prime. Okay, so that's the sort of corollary to it. What this says to us, if I take a number, so I take 397, and I go through all my divisibility rules, and nothing works, okay? Then what I have to do to determine if it's prime or composite is look at all the squares that are smaller than it, of those primes, all the prime squares. If it's divisible by any of those, then it's composite. So let's think about square numbers. So I have 1, 4, 9, 16. So that's the square of 1, the square of 2, the square of 3, the square of 4. But I don't need ones that aren't prime, right? Well, I do need 25 because that's a 5. I don't need 6. I need 7. It's 49. I don't need 8. I don't need 9. I don't need 10. I need 11. That's 121. I don't need 12. I need 13, which is 169. 14. I don't need 15. I don't need 16. 17. What's 17 squared? 17 squared, I don't know off the top of my head. 289. 17, it's still smaller. 18, I don't need. 19 squared is 361. 20 squared is 400, so I don't need to go that far. So here's the thing. I can test 397 with my divisibility rules, 0 through 11. And then, if none of those work, I test numbers that are prime, squared, as long as they are smaller than this number. If none of these work either, then it is prime. All right, so see if it's prime or not. I don't know. You tell me. It doesn't divide by 2. It doesn't divide by 3. It doesn't divide by 4, not 5. Definitely not 6. Does it divide by 7? You'd have to test that. You'd actually have to do the work, but it doesn't. Doesn't divide by 8. Doesn't divide by 9, not 10. Does it divide by 11? Nope. So now go through. Is it divisible by 9? Well, we already know that, so we don't have to do any of those. We don't have to do that one. Is it divisible by 25? Well, no, it doesn't break up into quarters. That doesn't make sense. Is it divisible by 49? Well, no, because 49s, if we add by 49s, it gets one less for every 50, right? So maybe 49 times 8, it gets me 392. That's not going to work. 121 isn't going to work. That's 363. 169 doubled isn't going to work. 338. And then these two, it's not going to divide evenly. They're bigger than half. So this is prime. All right. A couple more things. There's this thing called the sieve of Rathenus. It is prime numbers. It's developed a long, long time ago. It is something you inevitably do with kids in middle school. Basically what you do is you follow these rules. You write down all the natural numbers from 1 to whatever, 100, 50, 40, doesn't matter. You cross off 1 because it's a unit, it's not prime. You circle 2 because it's the smallest prime number. And then you cross off everything that's a multiple 2 because it's even. You circle 3 because that's the next prime. And you cross off the multiples of 3. Then you circle the next prime and cross off all its multiples. And then you circle the next one and cross off all its multiples until as far as you want to go. So look. So we cross off 1. It's a unit, right? We circle 2. We cross off all the even ones because we already dealt with them. going to be a little more efficient here. So by even numbers. We circle 3, and then we cross off anything that's a multiple of 3 that isn't already crossed off. Okay, then we circle 5. Any multiple of 5 that isn't already dealt with, we take. 7, same thing, 14, 21, 28, we got them all. Then we go to 11. We got all those. We go to 13. Got all those, and we keep going. Okay, if our list went longer, we'd have more things to cross off. But what happens is slowly but surely, your list is only made of numbers that are prime. Here's the thing. There is no formula for primes. There is no like quick, smart, quick way to tell if something's prime. If there was, I would have done it for you already. This is why things like this happen. There are computer programs that find primes this way, okay? As a part of all of this, a perfect square is a whole number that is a square of a whole number, right? A non-zero number, whole number, is a perfect square if and only if it has an odd number of divisors. Well, think about what that means. So think about a perfect square, right? Think about 16. What are the things to divide into 16? Well, it'd be 1 and 16, 2 and 8, 4 times 4. Think about 25. 1 and 25 and just 5. Think about 36. 1 and 36, 2 and 18, 3 and 12, 4 and 9, and 6. Interesting. Here's the thing. What happens with a perfect square is that it always has that one factor that's used twice. That's the nature of a perfect square. You squared that whole number. That means it's going to have an odd number of divisors. The only numbers that have an odd number of divisors like that are perfect squares. So if you go down a list and it says find how many divisors, and you get a number that's odd, you know that that number is a perfect square. Interesting. This isn't a way you can find really big perfect squares without actually multiplying really big numbers together. You can look at the number of divisors. All right. There are infinitely many primes, but there's no formula to find them. What you do is you use the primes you know to get to the next one. There's something called Mersenne primes. The way they get to them is to find 2 to the power of n minus 1, where n is a prime. But you can find the next prime that way, but if you don't know the prime to start, you can't get to it. There's also something called Sophie Germain primes, and she finds them by this. 2 times p plus 1, where p is prime. If you don't know the prime number to start with, we can't find the next one. That's the thing. There are people that spend their entire careers in math, like whole jobs, government jobs, all kinds of jobs, working on things with prime numbers, because prime numbers have lots of uses. They help build codes and all kinds of things, but you have to discover them. Okay, so this is the end of this section. Thanks. Move on to 4.3, and we will talk soon.